everybody, and welcome to this month's Night Sky News for September 2020 with me, astrophysicist Dr Becky Smethurst. This is the show where we look ahead at what you can see in the night sky in the coming month, and then also chat about what's happened in space news in the last month. We've got chapter titles if you want to skip ahead to any particular point, and any article or image or video, whatever I mention in the video, will also be linked in the description below as well. Without any further ado, let's start by looking up. Alright, so if you're new here, you won't know that my favourite thing to see in the sky ever is what I call a toenail moon, or a crescent moon, whatever you want to call it. And this weekend, from the 18th to 21st September, we're going to have a beautiful toenail moon in the west, just after sunset, looking absolutely gorgeous. Then next week, on the 24th and 25th of September, we've got the moon pairing up with Jupiter and Saturn, just like we had last month. And this is one of my favourite things that can happen in the night sky, that's something that's incredibly easy to spot, like the moon, because it's so bright. I would hope that everybody can probably at least attempt to find the moon in the night sky. It pairs up with something that's much harder to spot, at least if you don't know what you're looking for anyway. So on the 24th, the moon is going to be very close to Jupiter in the sky, which will be essentially the brightest thing after the moon. So you should be able to spot which sort of thing that looks like a star, but is actually a planet, is closest to the moon on that night. And then on the 25th, the moon will be closest to Saturn, which will be a little bit fainter than Jupiter because it's further away and look a little bit yellowish. But Jupiter and Saturn are a beautiful pair in the night sky at the minute. And so if you don't know what you're looking for, next week, 24th and 25th, this is a great time to look for them. Then from the 26th of September onwards, sort of into the first week of October, Mercury should be visible in the night sky just after sunset in the west. Now, Mercury is a very difficult planet to spot because it is so close to the sun. So we only ever see it just before sunrise or just after sunset, when the night sky is still pretty bright. You know, the light from the sun sort of glares out any of that reflective light from Mercury. So where you are on Earth is actually going to affect how easily you're going to be able to see this, because it depends how high Mercury is going to be above the horizon from your perspective. If you're in the southern hemisphere, it's actually going to be much easier for you because Mercury should be a lot higher in the sky compared to, say, where I am in the UK, where Mercury is actually going to be pretty low on the horizon, so it's going to be very difficult for me to pick out against the glare of the sun. Essentially, the closer you are to the equator in the northern hemisphere, the better chance you've got. And if you're in the southern hemisphere, you should have a very good chance of spotting Mercury. Then on the sort of 2nd and 3rd of October, we have another pairing of a planet with the moon, this time Mars, which I know, it's not my favourite planet, Saturn's my favourite planet, but I know it's a lot of people's favourite planet. So this is a good one to look out for if you've never been able to spot Mars in the sky before. Has a sort of reddish sort of tint to it. So on the 2nd and 3rd, find the moon, and then you should be able to find Mars probably just below it. Now, again, this depends where you are on the planet. The further north you are, the more Mars will appear to swing below the moon. But if you are incredibly lucky and you live sort of right on the tip of South America, then you will actually see the moon occult Mars, which essentially means the moon will pass in front of Mars on the sky and you will see Mars disappear and then reappear on the other side. So for example, Santa Cruz in Argentina, you will see Mars disappear at 11:18 p.m. on the 2nd and reappear at 12:18 a.m. on the 3rd of October. If you do live in that area and you want to find the exact times for your location, there will be a link in the description where you can put that in and find the exact times. All right, that's enough for looking up. Let's come back down to Earth and chat about all of the space news that's been happening in the past month. So on the 22nd of August, we recorded the closest an asteroid has ever sort of flown past Earth before, at least that we know of. It was an asteroid about the size of a small car, and it came within 1,380 miles above somewhere over the Indian Ocean, which, to put that into context, is about 22 times the height that a plane flies. So it was pretty damn close. And this is what obviously fills people with a little bit of anxiety. But for me, I'm like, well, at least we're spotting the little things, you know? Like, at least we found the small things that if they did impact with Earth, you know, would barely have any impact. You know, people would probably not notice. The wheelie bins outside might fall over. You know, that's about it. Whereas if we're spotting those little things, then we're obviously spotting the big things as well. We know that the asteroid sort of hunting missions on Earth, with some telescopes here on Earth, so the surveys and also sort of those in space on the lookout as well, they're doing their job and they're finding these things, and we can all sleep easy. Now cast your minds back to July, and if you remember, we had the beautiful Comet NEOWISE gracing our sky, and if you were very lucky, you managed to snap a picture of it, whether that was on a phone camera perhaps, or maybe even something a little bit fancier. We were all proud of the images we got. You know, it was even snapped from the International Space Station as well by astronauts on board. So I think a lot of people around the world managed to get what they considered was a great shot of Comet NEOWISE, but we have all been put to shame this month by the Hubble Space Telescope's image of Comet NEOWISE. Now you might be thinking, Becky, this looks nothing like a comet. And that's because it's focused on only the central part, you know, right in the middle in the nucleus, which we call the coma. This coma is essentially made of the gas that's escaping from the comet. So as the comet gets closer to the sun, a lot of the ice in the comet melts. It releases a lot of the gas that's sort of trapped in pockets in the rock. And then that gas sort of condenses to form an atmosphere around it. It's then sort of the solar wind or the sort of radiation coming off the sun that then hits that gas and sort of sends it streaming out in a tail away from the sun. And that's what we sort of see as the comet in the sky. There's a couple of things that this Hubble Space Telescope image shows. First of all, it shows that the nucleus of the comet is still intact, which is not always the case after comets pass by the sun. You know, all that melting ice and escaping gas can actually cause comets to break apart, like we saw with Comet Atlas earlier this year, that people got excited about, thinking that that might grace our skies. Turned out to be NEOWISE saving the day in the end after Atlas broke apart. The nucleus itself is actually too small to see in this image. It's actually only about 4.8 kilometers across, about 3 miles, whereas the coma is like 18,000 kilometers across, about 11,000 miles. And so what you're seeing is actually that at least it's still whole. Even though you can't see the nucleus itself, you can see that it's not broken up into many pieces like the Hubble Space Telescope image of Comet Atlas. You can also see that the gas and dust has a sort of certain colour, and the colour reveals the elements that make up the material that's coming off the comet, which is very exciting because that's material that's probably been trapped since the very early formation days of the solar system. And so by studying images like this, we can figure out conditions in the early solar system. So researchers are studying this image right now, figuring out, you know, what are they seeing and what is that telling us about the solar system. So I'm sure when that paper comes out in a couple of months, maybe, you'll hear about it right here. All right, so that was a nice, pretty picture, you know, just to get us warmed up before we get into, you know, whether the sun was born with a twin or, you know, LIGO's biggest black holes it's ever detected. But as usual, there was so much space news. I had to pick stuff for this video, but the rest I'm going to talk about on my Instagram stories. So if you want to hear about Jupiter's 4 Galilean moons and how they might be heating themselves to provide the right conditions for life, or if you want to hear about how rust has formed on the moon, despite there being no oxygen on the moon, then head over there to my Instagram stories. One of those will go up tonight, just as this video goes live, and one will go up over the weekend. If you're watching this video later, they're saved in a highlight on my profile as well, so go check them out there. But anyway, a paper that massively caught my eye this month was this one by Siraj and Loeb from Harvard. Now, these two authors are big supporters of the Planet 9 theory, that the solar system has a 9th planet, no, not Pluto, but another one that's way out past the orbit of Neptune, something like 400 to 800 times further away from the sun than Earth is, weighing in at around 5 to 10-ish times the mass of Earth. Now, it's still a hypothetical planet though, because, well, it's never been observed. But if it existed, it would nicely explain sort of the strange clumping of orbits of the dwarf planets and asteroids that are found out past Neptune. There have even been some that have suggested that the reason we haven't found Planet 9 yet is that it might be a black hole about the size of a tennis ball, which I am so on board for. It's ridiculous. I want the solar system to have a pet black hole. Now, this Planet 9 hypothesis is very attractive because it does explain a fair few things about the solar system that seem a little bit odd and quirky. But one outstanding sort of question for it is, how did this planet form out there? Like, how did a planet that massive get to be at that distance? Because everything we really see beyond the orbit of Neptune is essentially just rubble, right? It's planets that didn't really make it that big, like poor Pluto, dwarf planets as well. It's little clumps of asteroids. It's just the leftover stuff from the solar system. Now, there's a couple of ideas of how that planet could have got out there. One of those being that it was due to planetary migration, i.e. it could have formed further in towards the sun, and then perhaps with, say, an interaction with Jupiter, it got flung out way out to the edge of the solar system. That's something that I did a video on last week on planetary migration, so check that out if you're interested. It's all about how sort of Saturn held back the reins on Jupiter so the same thing didn't happen to Earth, and we didn't end up either flung out of the solar system or somewhere out on the edge. The other idea for how the planet got out there was that it actually is sort of a captured rogue planet. So if a planet that was forming around a star did get ejected through an interaction with, say, something as massive as Jupiter and did get flung out into interstellar space, and then, on its random journey through interstellar space, it encountered the sun's gravity and got captured around the sun. Now, as you can imagine, a random planet sort of wandering through interstellar space being captured by the sun is not that likely. The planet has to be on just the right trajectory to be captured into an orbit rather than either being sort of flung into the sun or just sort of like what Oumuamua did in our own solar system, where it sort of flung around the sun and was shot back out again. And so it's one of those things that everything has to be just right for it to happen. However, the probability of a planet being captured like that does go up if you have a binary system of stars. That's when you have two stars orbiting each other. So essentially the gravity around those two stars is always in flux. It's always changing. And therefore you've got much more chance of capturing anything that happens to be on a flyby because of that changing gravity. So what Siraj and Loeb are suggesting is that when the sun formed, it could have formed with essentially a twin. It could have been a binary star in the very early days of the solar system, which would have increased the likelihood of capturing Planet 9. Now, that idea isn't as crazy as it initially might sound, because the sun is actually a bit of a rarity in the Milky Way in the fact that it is just a single star. The majority of stars in the Milky Way actually are in binary, tertiary, or more sort of star systems. In fact, 50% of sun-like stars are thought to be in either 2, 3, or more systems. So it's not unlikely that in the very sort of dense cloud of gas and dust that the sun formed from, it did originally form with a companion star that was perhaps almost identical to it. This idea would also help explain the Oort cloud as well. This is a sort of spherical shell of icy, rocky rubble way out from the sun, even beyond what's considered the edge of the solar system, sort of the sun's little protective bubble of the heliosphere. We don't really know much about it. Voyager 1 is scheduled to reach it in about 300 years or so perhaps we'll know more about it then. But a companion to the sun could explain all that rubble that we see in the Oort cloud if that companion star formed in that gap between sort of the edge of the heliosphere and the sun's influence and the edge of the Oort cloud. Now, obviously, we don't see a companion star to the sun there today.
Obviously.
So what the authors suggest was that as the sun and perhaps its little companion star made their way out of the nebula, the gas and dust cloud that they were born in, there was some interaction that essentially ejected that star out of the nebula and out of the binary system that the sun had found itself in. That ties in nicely with some work done by Adebekian and collaborators back in 2018, who found a twin of the sun about 184 light years away. So with that result, especially, this idea that the sun was born with a twin doesn't seem that far-fetched anymore. But, you know, if we wanted to take it from quirky hypothesis to accepted scientific theory, then we'd actually need to go about proving this some way. And so what the authors of the paper this month have suggested was that if this actually was the case and the sun was born with a twin, we wouldn't just have planet 9, we would have this whole host of captured planets out at roughly the same distance that have been shepherded there by the sort of gravitational interaction between the sun and its twin. Now, we obviously haven't found planet 9 yet. It is very faint because it is at such a large distance. You know, there's just such a large area of sky that we could search in for it. It makes it very difficult. But if we could find planet 9, and we also then found this whole host of other objects at a similar distance that would be probably these captured rogue planets, then it would be very likely indeed that once upon a time, the sun had a twin. And finally, the result that, well, it took the astrophysical community by storm this month, and that was LIGO's announcement of its biggest black hole merger ever discovered, with a remnant of 150 times the mass of the sun. So on May 21st, 2019, LIGO and Virgo both detected ripples in space-time that lasted just 1/10 of a second that were most likely from the merger of two black holes. Now, after the first detection of one of these ripples back in 2017, it just seems like LIGO is detecting these ripples just basically all the time, right? These ripples that can be best explained under Einstein's theory of general relativity by the merger of two black holes. And so the fact that LIGO has been detecting more and more of these means we're building up this big population of them. We can get really good statistics on them and understand them better. So what's so special about this one? Well, it's the biggest ever detected. The two black holes were 85 times the mass of the sun and 66 times the mass of the sun, leaving a remnant black hole of about 142-ish times the mass of the sun. Now, the fact that it was 142 times the mass of the sun, the remnant that we think has been left behind in this merger, was the thing that got everybody very excited. Because at that mass, it puts it in the very elusive category of intermediate mass black holes. So we have a lot of things that we class as stellar mass black holes. These are things that are roughly the same masses of stars, you know, sort of like 3 times the mass of the sun and up. And they form in supernova. So when a star runs out of fuel, when it runs out of hydrogen gas to burn in its core, it goes supernova. It throws off its outer layers into outer space, and the inner core, where all that sort of fusion of hydrogen together to make helium was happening, that all collapses down under its own gravity to give you a black hole that's sort of like tens of kilometers across or so. And we see these all across the Milky Way. We see them either orbiting other stars, and so we sort of get little blips as the black hole passes in front of the star, or we even see the material that's sort of spiraling around and getting eaten by the black hole. That material gets so hot that it glows in X-rays, and so we know that they're there from observing the X-rays in the Milky Way as well. Then you've got supermassive black holes that we find in the center of all galaxies across the universe. They're the things that I study in my research, and I bloody love them. And they can be anywhere from tens of thousands times the mass of the sun to tens of billions of times the mass of the sun, all in a space that's about the size of the solar system. Then you've got, in between supermassive black holes and stellar mass black holes, you've got this category of intermediate mass black holes, anywhere from sort of 100 times the mass of the sun up to thousands of times the mass of the sun. But we've never found anything of that mass. And so it's kind of like the missing link. There's a sort of mass gap between the sort of everyday stellar mass black holes we find and the supermassive ones that we find in the centers of galaxies. You know, how did those supermassive black holes get there? Did they grow from stellar mass black holes? In which case there should be lots of intermediate mass black holes everywhere. Or did they form, you know, very early in the early universe as a sort of direct collapse black hole from a cloud of gas that sent it, you know, tens of thousands times the mass of the sun right from the very beginning. But sticking to topic, the big question for intermediate mass black holes, is it just that they don't exist, or, you know, they're very rare, not very common, or is it that they're just incredibly hard to spot? So the LIGO result is exciting for 2 reasons. First of all, for showing that, okay, intermediate mass black holes can exist, at least under the right circumstances, where you have these two other black holes merging together to give you something that's an intermediate mass. The second reason is because the two black holes that merged together in the first place were also in something we call a mass gap of the stellar mass black holes. So especially the 85 times the mass of the Sun one, but also the 66 times the mass of the Sun one to some extent as well. You would never expect to get a black hole that big from a normal star going supernova. As soon as you get up to stars that are somewhere 130 times the mass of the Sun to sort of 250 times the mass of the Sun, we're talking like really, really massive stars here, we think they just skip supernova altogether. And instead, when they run out of fuel, they essentially undergo this runaway thermonuclear actual explosion and blow the star apart completely and don't leave any remnant behind at all, not even a black hole. So there's this theoretical upper limit to how massive of a black hole you can form in a supernova when a star dies. And depending on what model you use for how stars evolve, you get somewhere between sort of 45 to 60 times the mass of the Sun for that upper limit. And yet here we've got two black holes that merged that were 85 times the mass of the Sun and 66 times the mass of the Sun. So it's very, very exciting not only to get something that was an intermediate mass black hole to end with, but also to start with two black holes that maybe shouldn't exist, but obviously clearly do. So one of the papers that came out from the LIGO and Virgo teams this month essentially went through all the reasonable possibilities to explain how these black holes got that massive to start with. And so one of the ideas was that maybe you had a cluster of stars and there was lots of massive stars in that cluster. They all went supernova, gave you normal sized black holes, which then all merged together in the cluster under gravity. Or perhaps you had runaway merger of primordial black holes, these tiny black holes that formed at the beginning of the solar system. And that's how we've ended up with these much larger black holes than expected. Or perhaps even that the merger wasn't of two black holes that massive, and instead it was of black holes of much smaller mass that were maybe on much more elliptical orbit, like an oval-shaped orbit that masqueraded as more massive black holes on a circular-shaped orbit. As always in astrophysics, I think it's more data needed. You know, we need to observe more of these mergers that give us these intermediate mass black holes to really understand them as a population as a whole and get more information from all of them. That will come in the future with new gravitational wave detectors like the ground-based Einstein telescope or the Cosmic Explorer, or perhaps even the space detector that's being built, LISA, as well.
Tomorrow.
Hey, Editing Becky, checking in here the next day. So I thought I was done filming. I thought I was completely done editing this video as well. And then the Royal Astronomical Society went and announced that they detected a molecule in the atmosphere of Venus that might be produced by life. Yeah, this is big, big news. And we have to chat about this. Okay, so if you had asked me last week, where was the most likely place in the solar system that we would find possible signs of life? My answer would not have been Venus. So this paper by Greaves et al. Was just announced by the Royal Astronomical Society, and essentially what they found is phosphine, PH3, one molecule of phosphate with three molecules of hydrogen, making a molecule in the atmosphere of Venus. Well, why is that exciting?
Phosphine gas. What about it?
Because after going through all the possibilities for how that phosphine got there, the most likely hypothesis right now is that it was made by tiny microbes living in Venus's atmosphere. So what they actually detected was that when they split the light from Venus into its component wavelengths or colors, one color that is generally associated with phosphine was missing. Essentially, like the light around that point, instead of being flat, there was a big dip that essentially said phosphine is there absorbing that very specific wavelength of light. And the wavelength that was spotted was around about 1 millimeter or so. It's sort of in the like infrared to sort of microwave regime of the electromagnetic spectrum. Now, this was first spotted all the way back in 2017 in data from the JCMT telescope on the summit of Mauna Kea in Hawaii. But that data wasn't the best. It was a little bit noisy, and although they were sure of the detection, it wasn't enough to make a bold enough claim that they wanted to. So they also then got in 2019 data using the ALMA array of telescopes in the Atacama Desert in Chile. And that gave much nicer data. It wasn't as noisy. Still obviously had some noise in it, but it meant that they could be very confident of that detection of phosphine in the atmosphere of Venus. Now, ever since that detection back in 2017, especially since 2019 when that extra detection confirmed what they'd originally found, the astronomers have been trying to think of all the different processes they could that were known of that produce phosphine, and then try and rule them out if they could. Now, on Earth, there's two main ways that phosphine is produced. The first is by humans in industry. It tends to be used in farming as a pesticide. It's also used to construct semiconductors, sort of like microchips that go in all electronics as well. And then the second way is by microbes, specifically microbes that don't need oxygen to survive. They tend to be found sort of where organic matter is breaking down. So I've heard that they're found, on the bottom of ponds where there's little sort of algae and all that kind of stuff. They're found in penguin poo as well, and also in badger stomachs. That was a list I saw. What an array of places that we find phosphine there, and apparently Venus. Now, we're pretty sure that industry and farming is not happening on Venus, but there are some other natural ways that phosphine can be produced, including volcanoes and geological processes, lightning striking the atmosphere and sort of acting as a catalyst, and then also sunlight also causing the production of phosphine, very similar to how sunlight causes the dissociation of an O2 molecule on Earth, and then that causes the production of ozone, O3. Kind of a similar process to produce phosphine, possibly on Venus. Now, what the astronomers did was went through all those processes and went through how much phosphine could they realistically make, and would that be enough to explain what we've observed? Because from the amount of absorption they saw, you can then infer, okay, how much phosphine is in the atmosphere? And they found that there was about 20 parts per billion of phosphine in Venus's atmosphere. And all of those natural processes, whether geological or something to do with sort of sunlight, none of those could give you enough phosphine to explain what they'd observed. And so, having exhausted all other options, the tentative conclusion, which is still a hypothesis at the minute, is that perhaps it's microbes living in the upper atmosphere of Venus. So don't let any of the news headlines sort of fool you over the next couple of days. This paper is not claiming it has detected life in the atmosphere of Venus. It is claiming a detection of phosphine. And after going through all of the possibilities, the most likely one at the minute is that it could be microbes. But there is a long way to go yet before that hypothesis turns into accepted theory and we start teaching that there's life on Venus in schools and at universities. One question is actually how those microbes are surviving in Venus's atmosphere. Okay, yeah, they might be some of the microbes that don't need oxygen to survive, but what about, the hostility of Venus's atmosphere? We know that Venus is the hottest place in the solar system. It's incredibly acidic as well. But it's thought that at the top of Venus's cloud, or at least the cloud layer, the pressure is very similar to Earth's atmospheric pressure, and the temperature is sort of a comfortable 30 degrees. The only problem is that Venus's clouds are made of 90% sulfuric acid, which is obviously incredibly corrosive, and so that would still be a hostile environment for a microbe to live in and not be dissolved by acid. So there's a lot of work still to do, not just for astronomers, to make more observations of Venus, perhaps look for more of these biosignatures that might sort of signal if microbes do exist, but also for astrobiologists to work out, how a microbe could actually survive in such conditions, but also for the geologists and the chemists to go back over, well, is there other ways that phosphine can be produced that we haven't thought of yet, that maybe we've overlooked. So I know people would like to probably think that the detection of life elsewhere in the universe will come from little green men or, you know, little piano tunes, Close Encounters of the Third Kind style. But in fact, it'll come from these biosignatures, because if we're going to detect anything around, you know, in an exoplanet, around another star in our Milky Way, then it's going to be something like this. We're going to detect the absorption signature of a molecule that's there that perhaps we can only explain if that gas or whatever it is was created by life and not some geological process. But to do that, we need to exhaust all these other avenues that these molecules and gases could be produced by. But that's probably going to be in the future, especially after the James Webb Space Telescope launches. But in the meantime, I think there's going to be a flurry of new observations and results about Venus, and maybe even we'll see, you know, instead of a load of missions going to Mars like we've seen in recent years, we might see a pivot and sort of being like, okay, let's send a load to Venus instead, because that's now the more interesting place. Who knows? Now, if you want to hear more about this result, I'll actually be interviewing the lead author on this paper, Professor Jane Greaves from Cardiff University, for the Royal Astronomical Society's podcast that I co-host, the Supermassive podcast. That will be out next Friday, the 25th of September, and there is a link in the description below so that you can find it wherever you usually find your podcasts. All right, is that it for space news now? Because I need to chill out and get this video uploaded. So, you know, universe, no more detections of life in the solar system, please. At least for the next 3 days. Now, as always with Night Sky News, we have covered a lot of topics in this episode. Everything from comets to the sun forming to black holes. And some of those you might not be familiar with as others. If that is the case for you, then I have the perfect thing for you, because this week's video sponsor is Brilliant. Brilliant is a website with courses on everything from science, maths to computer science that help you to learn in a very interactive and fun way. Most importantly, just engaging you with the content so that you really learn by doing. They have a treasure trove of astronomy courses on Brilliant, from understanding the night sky with the movements of the stars and the planets to the life cycles of stars as well. So this one would be particularly great to take if you're intrigued to learn more about the formation of black holes after our chat about how black holes form in supernova to give us the stellar mass black holes that we see through the Milky Way. If that sounds like something that you would be up for, then head to brilliant.org/Dr Becky. That's DRBECKY, or click on the link in the description below. The first 200 people that go to that link as well will also get 20% off an annual premium subscription. If you head to that link, you are actively supporting me and my channel. So a massive thank you from me to you if you do that. And also a massive thank you to Brilliant too for sponsoring this video. That's it for this month's Night Sky News. I will be back next week with another fun video on something to do with space. But until then, roll those bloopers. Hello everybody, and welcome to this month's Night Sky News for Bubble. I see a toenail moon rising. I see the flowers on the run. That's about 1,380 miles above the Indian Ocean. And to put that into context, but a companion to the sun could actually explain the Oort cloud. But a companion to the sun could actually explain the Oort clouds. Blah. Sister, sister, never knew how much I missed you. Solar sister, sun had a twin, and now we missed you. And they form from supernova. So when a sun